All right. I had mentioned in the last video that I was going to do graphs of spirals at the end of this section. Even though they do show up at the end of this section in the book, I'm actually going to change that. I'm going to skip talking about spirals. It's an interesting graph to look at, but it's the least important of the ones that we're going to be talking about. So if you want, you can look at that in the book. I don't think I gave any homework problems on spirals, so it shouldn't really affect anything. The last type of curve we're going to talk about, the last type of graph, is what's called a rose curve. Now, these are cool little graphs. We call them roses because the graphs look like flowers. We even call these loops petals, just to kind of keep with the flower theme. Rose curves come in a couple of different varieties. It's interesting, actually. They can be of the form r equals sine of n theta, or r equals a times cosine of n theta. And whether it's a sine or a cosine, we'll get one of these shapes, one of these sort of rose shapes, but there's kind of two other varieties that we get. So the n here is assumed to be some positive integer, generally larger than 2. If it was equal to 2, then, sorry, it could be 2. But the distinction that we make is whether n is even or odd. In the case where n is odd, the number that's there determines the total number of petals that the rose is going to have. So our last example that we're going to do down here, you'll see I edited it. It's a 3 theta down here. N in this case would be 3. Because 3 is odd, that's going to mean that we have a total of 3 petals. In the event that n is even, we actually end up with 2 times n, the number of petals. So in this case here, 4 is an even number. Because it's even, the graph of the rose that I get from this is going to have 8 petals, not 4. So we double this if it's even, we keep it the same if it's odd, and that tells us the number of petals that we need. Beyond that, you'll see there's lots of symmetry in these graphs. You can run them through your symmetry tests. But I want to also pay attention to the fact that the pole seems to be a point on either of these graphs, which means that if I set r equal to 0, I'll end up with a solution. Also, the tip of each one of these petals is the furthest any point on the graph gets from the pole. So those tips, those petal tips, are going to tell us what the are going to come from the maximum or minimum values that we get. So looking at this first graph, I can see that I would definitely have a 0, because if I set it equal to 0, 5 cosine of 4 theta, this implies that cosine of 4 theta equals 0, because 0 is between -1 and 1. That gives us a solution. So all that does is verify that the pole is on the graph. And then as far as max and min values, remember, what we're doing is just taking the cosine and swapping it out for either a positive or a -1. So for a positive 1, I would get 5 times 1, which is 5. For a -1, I get 5 times -1, which is -5. But in either case, 5 or -5 in polar coordinates, that represents a point that's 5 units away from the origin, or the pole. So what that means is that the tip of each of the petals, remember this is going to have a total of 8 petals, the tip of each of these petals is going to be 5 units away from the pole. Now, in addition to that, I'm going to use the fact that this is an even number. It's 4. And again, like we said, we have double the amount of petals on this rose. So I should end up with 8. And here's where we pay attention to the difference between sine and cosine. Cosine, notice if I plug a 0 in for theta, cosine of 4 times 0 is cosine of 0. That gives me 1 times 5, which is 5. So the first petal tip is going to correspond to the angle 0. And that's what we're seeing here. An angle, if the angle is 0, that's like the positive polar axis. You see your first petal right there. So I know that my first petal is going to be 5 units away from the pole. I have to count that out. I'm going to go 1, 2, 3, 4, 5. Okay? And what I'm going to do is just put points for the petal tips before I do anything else. Now, you'll notice also, because of all the symmetry in this thing, these petals are evenly distributed in this circle. So that this, right now the circle I'm looking at is r equals 5. But the points are going to be evenly distributed. There's a total of 8 petals, so there's a total of 8 points that I need to distribute around the unit circle, or sorry, around the circle r equals 5. The first one occurs when theta is equal to 0. Now, if I think of the total radian measure of a full circle, that's 2 pi. If I take 2 pi and divide it by the total number of petals, which is 8, I get pi over 4. What that tells me is that the spacing between each of these points, as far as the angle between them goes, is pi over 4. So I'll find pi over 4 and stay on this circle here. I'll have a point there. Add another pi over 4, that takes me to pi over 2. And then 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, and then 7 pi over 4. You see how those points are evenly spaced? And each one has an angle of pi over 4 radians between them. I got that, again, from taking 2 pi, the total number of radians in the circle, dividing by the number of petals, and that tells me how to space these things. So now I'm just going to create the petals, and I'm not going to be too concerned about it looking perfect. I have essentially all the important parts of this thing that I want. Okay. And these petals are not supposed to overlap with each other, so when you get towards the pole here, you want to make sure that you're not like crossing over one petal with another petal. But again, not worried about perfection here. Just need to make sure that these are properly spaced, that the petal has the correct orientation, and that the points are on the circle r equals 5 in this case. Okay, so again, notice the coefficient is what gave me the length of each petal. That's going to be the same thing that happens in this example down here. The graph of r equals 4 sine of 3 theta. Because 3 is an odd number, like we said before, we're going to have a total of 3 petals, and each one is going to have a length of 4. But the difference between sine and cosine with these guys is that the sine function, or if the sine function shows up in the equation here, the first petal will not be on the polar axis the way that it is here. You'll notice here the first petal is off that polar axis. So we have to come up with a way of determining where that first petal is, and then we can equally space the other petals similar to how we did it in the previous example. The key to this is to notice that this point here comes from a maximum value of our equation. So let's come over here for a second. I know that for this function, I'm not even going to go through the whole process as we did in the previous one of finding 0, max, min. I know that the maximum value is going to be 4. If I set r equal to 4, so 4 equals 4 sine of 3 theta, that tells me that 1 is equal to sine of 3 theta. Okay? Now that means, if I think about where sine is equal to 1, the first place in the unit circle where sine is equal to 1 is pi over 2. So I set the angle 3 theta equal to pi over 2 to give me a solution to this. Solving for theta by dividing by 3 tells me theta is equal to pi over 6. That's going to give me the first petal. So I find pi over 6, which is here. Go to the fourth circle. 1, 2, 3. I lost it. 1, 2, 3, 4. Right there. And that's where the point for my first petal is going to be. Now I need to figure out how to evenly distribute all of my remaining petals. And there's only 2 more petals that I need to get. Well, a total of 3 petals. If I think of the full circle as being 2 pi, and I want to divide that into 3 equal pieces, that's going to give me 2 pi over 3 spacing between each petal. Now my first petal, for my first petal, theta was equal to pi over 6. I don't know why I wrote pi over 4. This spacing here tells me what to add to this to get from this pedal tip to the next pedal tip. So the second pedal, I take theta and I take pi over 6 and add the 2 pi over 3 that we got in the previous example over here. So this would be 4 pi over 6 plus pi over 6, which is 5 pi over 6. That tells me where to put the next pedal. 5 pi over 6 is, let's see. Oh, you know what? I'm realizing I wrote this so small, or I had this typed so small that I'm actually reading that incorrectly. That's pi over 8 right there. I'm going to say pi over 6 is actually right there. So we're sort of just estimating here. 5 pi over 6, I'm going to put that, where would that be? Let's just say it's here. So I'm going to say that's pi over 6, 5 pi over 6 for the next pedal. Actually, I think it's going to be here. That's okay. My polar grid was not labeled the way that I thought it was, but that's all right. To find the third pedal, what I need to do is take my previous pedal, which was 5 pi over 6, and add this 2 pi over 3 to that to get the correct spacing. So again, this would be 5 pi over 6 plus 4 pi over 6, which is 9 pi over 6, or 3 pi over 2. That puts me on this axis, or sorry, at this point right here. Okay, so there's a couple of mistakes in here, but I'm going to put those pedals in now. Doesn't look great, but that'll work for what we need it for. Okay, and that wraps up section 10.4.